All right, let's begin. Good morning, everybody. Welcome to Algebra 2. We're continuing our run through the conic sections. We saw parabolas on Monday, those good old shapes we know and love from quadratic equations. We looked at circles yesterday, which were the most simple and straightforward of the conic sections. And today we're going to look at the ellipses that are, let's say, medium scale, right? A little bit more complex than a circle. They are literally a circle that has been squished, okay? But not as bad as the hyperbola. There's a reason we're saving hyperbola for next week, because that really throws a wrench in things, quite literally, with negative numbers, okay? But we don't have to worry about that for now. So, without further ado, let's take a look at what is an ellipse, what are its defining features and traits, what sets it apart as a conic section. Well, if you take a look at a picture of one, or actually, let me back up. Let me start with where we see ellipses. We see them physically all the time whenever you want to draw 3D shape, right? If I want to draw a can, okay? What I'm actually drawing is an ellipse, right? I know that this can, this object, right, is circular. Let me get a better example here, right? I know that this is a perfect circle on the top here, but when I look at it at an angle, you only see, you get the perspective view, and it looks like an ellipse, right? So that's the difference there. It's a squashed circle, and so it doesn't have a single dimension to it. Remember, a circle could be defined by its radius. You have a location where the center is, and then a radius to give its size. The ellipse requires two sizes. We call one the major axis, and the other is the minor axis. Literally, whichever one is bigger gets called the major axis. Okay? So notice the circle is more stretched horizontally than it is vertically. So the major axis is horizontal, the minor axis is vertical. Now, what's really cool about this is when you do that, you create, instead of a single center point of the circle, you actually create two centers of the ellipse, or rather, foci. It does actually have a proper center. It is still a symmetrical shape. So we have that center there, in this case at the origin. But we create now these two foci, which are two new unique points within the ellipse. And what they do is they create that distance relationship. Remember, we introduced all of these conic sections by measuring distance and midpoint. So the circle is defined as all the points that are the same distance from a single central point. The ellipse is all of the points that form the combined distance from one foci to the ellipse to the other. Okay? Let me make that clear with a new diagram here. We have an ellipse, and we have our two foci. I can draw to anywhere on this ellipse. Okay? And this distance here plus that distance there will always be constant. Right? That's what creates the ellipse. It is based on that definition of these matching distances. This sum of the distances is always the same. Even if I go all the way across and back. Well, actually, out, across, and then back just to this one. Okay? That distance out and back to the other focus creates the ellipse. And it is really, physically results in a lot of really cool things. One, you can draw an ellipse, much like you might draw a circle with a compass or a string and your pencil. You could hold the string down and draw a circle in one direction. For an ellipse, you need two pins, Right? Imagine you got some little thumbtacks there. And you take a loop of string around those thumbtacks, and then set your pencil point in there. And now you can work your pencil around, tugging on that string, always pulling it taut. This distance, of course, between the foci is constant. And then you add these two segments of the string. The loop of string can't change size. You get a non-stretchy string. And you just pull your pencil along, and you will draw out a perfect ellipse. The other cool thing they can do is similar to, let me clear all this out, similar to the parabola, right? There's a reason these points are called foci. Remember, the parabola took all incoming rays. If we had a parabola with this focus, it took all incoming rays and focused them on that focus, right? The ellipse does something similar, but it's all rays coming out of one focus will bounce around and land at the other focus, right? This is really cool. So if you had, say, this is typically embodied with sound waves more so. Yeah, I think, is it the Library of Congress itself? It's one of those rooms in Washington, D.C., where they have the ceiling is an elliptical dome. And the practical effect is if you stand right here and whisper very softly, somebody standing at the other one can hear you because your voice will bounce out in every direction, but it will always end up back at the other focus. Isn't that so cool? That's so weird. And so you can talk very softly. And so somebody standing, over here wouldn't be able to hear you because your voice, the voice wave, right, spreads out and dissipates. And so the tiny bit of that energy that they're actually able to pick up over here, that's not enough. But since all of that spreads out, gets bounced around, but it gets refocused back in, somebody here can actually pick up enough of it to actually understand what you're saying. Really cool. So that is the main features of an ellipse. Here then are the mathematical properties. We can, of course, set our ellipse to run either horizontally or vertically. And that is based on what direction the major axis is going. Which direction is largest? Okay, major axis is always the biggest one. And this can sometimes be confusing because it's not going to be consistent here. It's not like X and Y always the same direction. The major axis is not always vertical or always horizontal. The major is always the biggest one. And so we'll always be calling that 2A units. Okay, so the major axis, more properly, the length should be, right, the whole thing all the way across. It's a little too big. Okay, and likewise, the minor axis is distance across. So those correspond more with the diameters than the radius. You want the full axis length. But A and B here, notice length of axis is 2A. Where does that A come from? It comes from the equation. Okay? Take your circle equation, x squared plus y squared equals 1 for the unit circle. Before, we would have had a radius. So you could have taken x squared plus y squared equals r squared. Divide everything by r squared, right? And this would be 1 over here. This would be r squared. This would be r squared. But with the ellipse, you don't have the single radius. We have two different radii depending on which direction. So a horizontal radius versus a vertical radius. We'll call those A and B. And we've decided, by convention, at least within this text, we're going to use A will be whichever one is the biggest. So notice for the vertical ellipse, A stays here, and it's now underneath the Y. Okay? So whichever number, if you're given an equation that already has the numbers, whichever one is bigger, you call that one A, call the other one B. Right? It's probably the most confusing part of this, is switching A's and B's. I wish we had a better convention for it, but there's no other. Somewhere we're going to have to account for the possibility that one could be horizontal, one could be vertical. Okay, this is the convention we've got. And then look at this this length, the foci, where the foci are, that distance C, right? This is, of course, centered at the origin, so the foci is a distance C away from the center. If your ellipse was not centered on the origin, you'd still have this minus h minus k stuck inside there, and then your focus would be C from h comma k, right? But from the center, your focus is a distance C away. And this is really handy because it makes the calculation. Whoops, that's not the eraser. Oh, wait, no, I didn't want to get rid of the ellipse. Let's go back to this picture. Set up my foci here. And we'll set the center point right there. So we've got lots of things we can draw in. We have the, in this case, minor axis out here, so that'll be B. We have the distance to the focus there, that'll be C. And we have the major axis, half the major axis length is A there. What does this remind you of? It's a right triangle, folks. It's Pythagorean theorem. The only thing we've done is we screwed up the lettering here, right? And the A should be there and the C should be there. And, okay, whatever. Which letters you use doesn't matter. This is still the hypotenuse. A, the major axis, is always the biggest length inside the ellipse. If you can remember that bit, don't let the letters confuse you. The major axis is always the longest length inside the ellipse. Okay? Said it twice for emphasis. So use that combined with the power of creating a right triangle and the Pythagorean theorem, and you can work out the focal length, right? So focal length will just be Pythagorean theorem, square root of a squared minus b squared. And A and B then come directly from the equation. So if you're given the equation of an ellipse, you can find the focal length there, no problem. You can find the center, of course, will be h comma k straight out of the equation. If you don't see an h or a k, they are zeros. So then take your focal length, add that onto your center to get the actual location of the foci, right? Add and subtract in the same direction as your major axis, right? Any questions so far? Okay, I don't think I had. Yeah, so let's look at an example here. So we're going to go from graph to equation, and then we'll reverse it. We'll go back from equation to graph. Here we go. Here's an ellipse. They give us a couple of points. We know the origin is the center point. We can see the foci are in there at 0, 3. So right away we can read from this that our focal length C is 3. They give us the location of these points. They call that out 0, 6. Is definitely more than 1, 2, 3, 4, 5. Let's give that quick measure there. 5, that's going to be our minor axis. And our major axis, I'll just use the other side here, 6, is A equals 6, right? Can everyone see how we got those measures from the graph? If they did not give you the foci, that's okay. You can still get from A and B, you can calculate the foci, the focal distance, right, Pythagorean theorem, and fit those in yourself if necessary. Okay? This does not show up in the equation. We don't need it to write the equation. All we need from the equation is the center. That's 0, 0. Okay. We need the length of A, the major axis, which is 6. And we need the length of B. The minor axis is 5. So x minus h, which is 0, so nothing, squared divided by A or B squared, I'm not sure yet. We'll set it up by something equals 1. I'm not subtracting anything, so I don't need the parentheses. And now let's double check which direction was bigger, in the y direction or the x direction. That would be the vertical, right? The major axis here was vertical, so the 6 squared goes underneath the y, and the 5 squared goes underneath the x. All right, simplify those, 25 and 36 to get your proper full equation as they have done here. Clear as mud. For some reason, this textbook prefers to go A then B instead of X then Y. I prefer X then Y. I like keeping this order consistent and moving my A's and B's to where they go. The book likes to keep the A's and B's in this order and swapping X and Y where they go. You're adding here. The order doesn't matter, right? Addition is commutative that way, so don't worry about it. The important thing is 5 is underneath X, 6 is underneath Y. That's all that matters. Solve for, wait. Is B not actually 5? Oh, it's not. Well, I see what they did here. Nobody point out to me like, hey, wait a minute, Mr. Apple, that doesn't say 25, that says 27. How'd they get 27? Well, there's a reason they didn't call out this point right here. They didn't say, hey, this is 0, 5. It looks like 5. This is why reading off the graph is so difficult. Okay, so we got to use this as the proper. This is, B is not 5. B is some mysterious, slightly larger than 5 number, right? You guys should have known. There's no such thing as a 3, 5, 6 triangle. That would have been too easy. All right, so we know what we have. We do have the focal length here. Might as well clear that out because it's wrong. Okay, what do we know? We know A is 6. We got that much. We know the focal length is 3. We can read that. So now we got a Pythagorean theorem, okay, to get, in this case, they're using focal length. This is not classic Pythagorean. This is focal length and the 2 axes, right? Notice the subtraction there, to solve for the missing one, B. So B becomes, add B, subtract 9, right? B squared equals 27. And if you're doing this, honestly, do I ever need B by itself? If I'm just writing the equation, I only need B squared, really. So the square root of 27 is not an integer, but that's not an issue, okay? It only comes up if necessary. If something asks you, hey, what's the length of the minor axis? Absolutely, you got to put square root of 27. But otherwise, just put down 27. I only need B squared. Don't worry about it. All right, questions so far? we try another example? Kind of buggered that one up, didn't I? Right? We got too confident. We were like, oh, that looks like 5. It looks so easy. No, Mr. Apple, don't base your answers on what looks good. You got to go with what they actually give you. So let's try from the top. Here's an ellipse centered at the origin. Oh, thank you. That makes life so much easier. Excuse me. What do we actually know? We actually know a focus right here. So C is definitely 4. We know one of these axes over here is 6. Is that A or B? Well, let's approximate, right? 1, 2, 3, 4, not quite 5. And this is definitely 6. So this has to be the largest one. A's 6. Okay, so then we know A is always the largest, so 6 squared equals C squared, which is 4, plus B squared. All right, fill in our hypotenuse. We need to solve for B squared, so that would be 36 equals 16 plus B squared. Subtract 16 from both sides. B squared is 20. So if I wanted to know the actual distance for B there, it'd be the square root of 20, right? Or 2 root 5, right? 4 times 5 is 20, yeah, 2 root 5. An exact form, but I don't need B. I just need B squared for my equation, because my equation is always going to look like this. X squared divided by something plus Y squared divided by something equals 1. Now I just got to go which one goes where. The biggest one was 6. That was going in horizontally, so that goes underneath the X. X is horizontal, so 6 squared is 36. Underneath the Y squared goes the B squared, which we determined was 20. So I put a 20 right there. There's the equation of my ellipse. Okay.
So for the 20, we don't have to put it square root?
No, because the equation calls for B squared.
Oh, yeah. Okay.
Right? I need B squared in here. I don't need just B. You can find that out. I mean, we can determine, you know, okay. Just B would, of course, be the square root of 20, which is 2 root 5. We reduce that radical. But I never need this number if the question only asks for the equation. If someone asks for the length of the minor axis, then you want to call this up. But until you need that number by itself, don't worry about it. Okay, we are mathematicians. We are always as lazy as possible. Okay, do the minimum amount of work required. All right, now the only thing left would be to sketch the graph from the equation. And I don't think, I don't have an example of that here. So let me find the actual worksheet tonight. Here we go. So first page, there's a reminder of all your information. We've got equation from the ellipse shown. These first set of exercises, actually, they don't give you the full graph. They just already write out the information for you. Okay, so that's pretty nice. Whereas on the back here, we are actually creating the graph ourselves. So let's see what we can do there. Let's try one of these. Let's do number 4. Number 4 looks like the hardest. Right, so we'll do 4. If we can tackle 4, we can tackle anything, right? It's got more than just X and Y. Oh, shoot. We've got to complete the squares first. Oh, geez, more work. That's okay. It's okay. We can take care of it. It's just going to take longer. So breathe. Grab a snack, and let's have at it. I want the X's together. Let's put the X's together. 9. And factor out that 9. I would rather have just X squared. Minus 36 divided by 9, it leaves 4x plus some amount there. And for the y's, we're going to factor out a 6 y squared, this is positive, plus 12 divided by 6 leaves 2y plus some extras there. And all that is going to equal 12 plus my 2 blanks. I'm out of space on the page here. All right, completing the square. So we just take this b term, divide that by 2, and square it. So half of negative 4 is negative 2. Squared up is 4. Add 4, add 4. Half of 2 is 1. Squared is 1. Add 1, add 1. No, I did not add 4 and 1. I added 9 times 4. Oh, geez. Watch out for that. 9 times 4 is 36. 6 times 1 is 6. We added a lot more than we thought. Okay, but now we can reduce this down. 9 out front. We've got x, what was it? Half of negative 4 is negative 2, x minus 2 squared, plus 6 times y plus 1 squared. Oh, that needs a little bit more space. Equals, and 12 plus 36 is 48 plus 6 more, 54, right? Okay, now we have to divide everything by 54. We can't leave any numbers besides 1 over here. That's got to get to 1. So divide this by 54, and divide this by 54. And so those are going to help reduce out these numbers up top, and we'll be left with something in the bottom that'll give us our axes lengths, right? Or the half-axis length. So 54 divided by 9, 6. 6 minus 2 squared divided by 6, plus y plus 1. 54 divided by 6 is 9. Forgot my squared there. Close. 1. Okay, ignore the Glencoe Algebra 2 bit in the way, but there is my final form of my ellipse equation. So we can read off 3 things. The center point, major axis, minor axis. That's all we need. Let's go with orange here. So center point comes from these 2 guys. X minus 2. Remember, it is x minus h. So if it shows minus 2, h itself is a positive 2. So h is over here. And then y plus 1, y minus k. So minus negative 1. So k is down here. So our center point is down there at 2, 1. All right. Now our a's and b's, we only need a and b for the graph. But in the equation, we have a squared and b squared. So find out which one is bigger. That would be the 9, so that's a squared. This is b squared. So a is the square root of 9, which is 3. That's nice, and that's going vertically here. This is really throwing me off because they gave me a graph that is more horizontal than vertical. I feel like no, I must have screwed something up. They wouldn't do this to me, would they? They would. The book isn't that nice. Anyways, all right, so a is 3 in the vertical direction, so we're going to go from the center, 1, 2, 3, and 1, 2, 3. There are the top and bottom edges of my ellipse. All right, and if you want the coordinates, that's going to be 2, 2, 2, negative 1, 2, 3, 4, negative 4. Okay, and b is going to be a square root of 6, which is more than 2, but less than 3. All right, so it's going to be awkwardly here-ish, right? Over 1, 2, not quite 3. Something there, right? This is going to be 2 plus square root of 6. You know what? We can write it just like that. That's fine. 2 plus root 6, comma 1. And this will be 2 minus root 6, comma 1. Totally acceptable. And now we just play connect the dots. Remember, you want this to be kind of flat, just like with the circles. Here. So we loop around our ellipse there. I mean, it's kind of lopsided, but hey, that's pretty good for a first shot, right? There you go. There's an ellipse. It's graphed. Okay. Remember, the important part is just get those points listed, those critical points at the ends of your axes. Don't worry so much about the curve being nice and pretty.
So for the center, does that say 2, 1?
Say it again.
Does the center say 2, 1?
Yes.
Oh, well, wouldn't that be 2, 1?
Yes, you're absolutely right. Should be a -1. Oh, that's terrible. -1, -1, -1. Thank you. I did put it in the right place, though, right? Yeah, okay. Just forgot to write my negative. There you go. All right, any other questions on graphing an ellipse? Sketching an ellipse? No? All right, then with our remaining 15 or so minutes, go ahead and get started on the rest of the worksheet. Answer the questions as appropriate for your chosen study level. And let me know if you have any questions. I'll be standing by.